Okay, so we're going to finish up related rates. This will be the second video for this section. These are a little bit of the harder problems, so I'm going to do about 3 examples of some of the more difficult problems you'll see in related rates. So the first one I want to talk about is conical water cups provided at a water cooler dispenser have a diameter of 3 inches and a height of 4 inches. If water enters the cup at a rate of 1 inch cubed per second, how quickly is the height changing when the height of the water in the cup reaches 2 inches? So we have quite a bit to unpack here from this problem. So the first thing we need to identify is the when, or I mean, I guess it really depends, but it says the conical water cup provided water cooler dispensers have a diameter of, so first of all, what shape are we dealing with? We're dealing with a cone, right? And it has a diameter of 3 and a height of 4 inches, okay? Let's see here, diameter 3. So I just want to kind of highlight to you guys, this picture right here will not be provided normally. You have to come up with it every once in a while. If I find a problem that has a good picture, maybe in the exam or in the homework, it'll be provided, but sometimes you have to develop it on your own. So here we have, this is if the diameter is 3 inches, then the radius is 3/2 inches, right? Or 3/2. And then here we see the height is 4. Okay, so that we've kind of written out the dimensions of this cone. So now it says if water enters the cup at a rate of 1 inch cubed per second. So when you're pouring water into a cup, you're changing the volume inside the cup, right? So that's going to be, let's call that dV dt. And we know that that's 1. I mean, you can call it 1 inch cubed per second, but we're just going to call it 1 for now. And what are we trying to find? It looks like we're trying to find, it says, how quickly is the height changing? So that means we need dH dt. Let me adjust this real quick. There we go. So that means we're looking for dH dt. Okay, we need to know the change in height with respect to time. Okay, when, now notice it even says the word when, the height of the water in the cup reaches 2 inches. So we know that the height is actually 2 inches. So when we have h equals 2. Okay, so we have some information. And if we think back to the previous section, there's, some steps we have to go through, but one of the biggest things we have to know is we have to have some kind of equation that relates all of this information together. Okay, so because they're talking about a cone and we're trying to find the change in volume, something that has to do with height and something that also involves maybe a radius. Okay, we know the radius is r equals 3/2 and h equals 4 maybe. Okay, but that's not the when information. That's like the cup itself. Okay, so we need something that ties all this in together. So I think I'm going to try to use the volume formula for a cone, and this will be 1/3 pi r squared times h. Okay, so this is our equation that relates. Okay, so this is everything gets tied in together with this equation. Okay, however, there's a slight problem. We have 2 variables on the right side and we have the volume on the left. So you guys remember when we take the derivative of both sides, we're going to end up with a dV dt. We're going to end up with a dV dt. Somewhere over here, we're going to have a dr dt, and then plus, and then we're also going to have a dH dt. Now that's a problem because yes, we're looking for dH dt, and yes, we know dV dt, but we actually don't know dr dt. So we're going to have to think of something else. So what I'm going to try to do is I'm going to try, whenever you have too many variables, you can try to solve for the variable ahead of time. Okay, so I'm going to try to solve for r and substitute it in. Okay, so I'm going to rewrite everything in terms of h. So we are going to rewrite the volume equation in terms of h, okay? But in order to do that, I have to find some kind of relationship that will allow me to solve for one of the variables. Well, something hopefully you guys have noticed is right here, this is a triangle, and then right here, this is a triangle. So we actually have similar triangles. So whenever you have similar triangles, So whenever you have similar triangles, you can try to use proportions. So I'm going to use the proportion of 3/2 to 4. So I'm going to use the proportion of the radius to the height, which would be 3/2 to 4, as R is to H. Okay. Now, again, this is a little bit, I set it up nicely like this. Remember, proportions can be rewritten in multiple ways, but since R is the variable that I'm going to be solving for, it's in the numerator already, so it's kind of nice. So then this is going to become, let me see, 3/2 divided by 4 is really 3/8, right? Times H, and that equals R. Okay, so I now know R. So what I can do is I can take this and plug this right in there for R. Now this becomes volume equals 1/3 pi. Now R is 3/8 H squared times H. Now we don't want to DDT yet. We want to clean this up just a little. So V equals 1/3 pi times 9/64 H, what would that be? H cubed, right? So 9/64. We can do a little bit of canceling. This is 1 and this is 3. So we should end up with, let me write it over here so I don't run out of room. V equals, what would that be? 3 pi over 64 times H cubed. Okay. Now the reason I'm writing it as 3 pi over 64 is so in my mind, I know that this is a constant. So I don't have to use like a product rule or anything. I'm just going to use the constant multiple rule. So what I'm going to do is I'm going to DDT both sides now. Okay. So again, this is now over here. And when I DDT that, I end up with dV dt is equal to 3 pi over 64. That's just a constant. Times, take the power, put it in front, rewrite the h, reduce the power by 1, and then attach the derivative of the inner function, which is dh dt. Which is good, right? Because we're actually trying to find dh dt, right? We actually want to know it. And we ended up with a dv dt, but that's totally fine because we have dv dt right there. So now the question becomes, can we solve? Well, our job is to find out what dh dt is. So let me do a little bit of cleanup here. We have dv dt. Well, you know what? I'm going to rewrite this. This is worth 1. Now, this would be 9 pi over 64, but we know that h is actually the when information. They said h is 2. So we want to know what is the change in height when the height of the water is at 2, is it inches? 2 inches, yeah. So we're going to put 2 squared in here. So this would be 4 dh dt. Okay, so this can cancel. Oops, I'll do it in red. This can cancel, become 1. This will become 16. So then we're left with, I'm going to multiply right now by the reciprocal. So this would be 16 over 9 pi. And this would cancel with this, and this would cancel with this. And then I'm going to put a 16 over 9 pi here, right? So then I end up with 16 over 9 pi. Let me see. Let me make sure I didn't miss anything. No, I think that's it. Equals dH dt. Okay. So the rate of change is 16 over 9 pi. You know what? 16 over 9 pi, and I think it's what, inches per second. And that is dH dt. Okay. So this is how you can use similar triangles, which makes it, I believe also I've been told by a lot of people that have taken the AP test, they oftentimes will have a problem like this. The key is that you have to know the volume equation because if you don't know that equation off the top of your head, that would be difficult. If you're taking this class and we're not still on COVID and this is an online class, then obviously you'll have this in your notes next to you and you'll know how to do it. But if you were taking it in class, I would probably provide you with the volume formula if needed. But in general, this is one of the harder problems that you will see because it requires multiple approaches to solving the problem. You can't directly solve it. You have to replace a variable. And in general, that makes these problems a little bit more difficult. Okay, let me see. That's most of the problem right there. That way you guys can see most of it if you want to like screenshot it and take notes on it or whatever. Okay, so now let's look at another example. Okay, so it says a kite at a constant 150 feet above the ground moves horizontally at a rate of 10 feet per second. At what rate is the angle between the string and the horizontal? At what angle is the string between the string and the horizontal decreasing when 300 feet of string have been let out? Okay, so basically what they're saying is you're letting string out. This is the angle of concern right here. You know, as you let more and more string out, you know, this is staying at a steady height over here, but now the angle from there to there is smaller. And then if I went further out, the angle would be smaller and smaller. So they want to know what rate the angle is decreasing. Okay, so this is kind of a drawing, and I'm going to try to stick to the labels that are used in the graph. Okay, now the thing is what can relate lengths of sides and angles? Okay, what do we know about that? Well, if you guys remember correctly, we have sine, cosine, and tangent, right? So we know that sine of theta for this problem would be what? What would sine of theta? Isn't sine of theta opposite over hypotenuse? So opposite would be 150 over y. Cosine of theta would be x over y, and tan of theta would be what? So SOHCAHTOA opposite 150 over adjacent, which would be x. Okay, so these are kind of our three choices. Now we have to decide which one works. Okay, so the first thing is we should write down what we know for sure. Okay, so it says at what rate is the angle between the string and the horizontal decreasing when 350 feet of string? So we know the when is, we have y equals 350, I believe, or no, 300 feet. So y equals 300, because they're saying this is y, and they've let out 300 feet of string has been let out. So that's the when. Okay. It says a kite is at a constant of 150 feet. We know our constant, that is h equals 150. Or if you want to call it, a squared plus b squared equals c squared, or whatever you want to say, but we know that the height is always going to be 150. Okay, now we don't have an h in this problem. We should say the height. Oops, I think I spelled that wrong. Height equals 150, and this is not going to change, right? It's saying that it's at a constant rate. Moves horizontally at a rate of 10 feet per second. So we also know that horizontally would be like this, right? So we're going to say that that's our dx dt. And that they said was 10 feet per second. Okay, so we're good on that. So we have all this information. Now we need to think, okay? We need to think. If we were going to take the derivative of both sides of this equation, we would, we need to actually also, what are we looking for? We're looking for d theta dt, right? We need to know what this is. We need to know what d theta dt is. So if we were looking for sine theta equals 150 over y, we would end up with a d theta dt, but we would also end up with a dy dt. I don't have a dy dt to plug in. So I have a dx dt. So anything with a y in it, I can't use. So that means I can't use this one and I can't use this one, because I will end up with a dx dt and a dy dt, and I don't know how to deal with the dy dt. However, the tangent function has a theta and it has an x. Well, I know dx dt and I know d theta dt. So that's what helps me decide. So I'm going to set up the formula. This is my equation that relates tan theta is equal to 150 over x. Okay. Now, if you want, well, I guess that's fine. We can just leave this. This is actually 150 x to the negative 1, correct? That's a rewrite. So now I'm going to ddt both sides. So this will become, what's the derivative of tangent? The derivative of tangent would be secant squared theta, but then you just took the derivative of a tangent theta with respect to t. So we must attach the derivative of theta, which is d theta dt. That's the chain rule, right? And then this equals, the derivative of this would be negative 150 x to the -2, but I just took the derivative of x with respect to t, so I have to attach a dx dt right there. Okay, take the power, put it in front, rewrite the inside, reduce the power by 1. So let's see how we're going. This is slightly, I'm doing it differently than I did in my notes. In my notes, I converted it to cotangent just so I didn't have the x in the denominator. It was just in the numerator, but we'll see how it goes from here. So now my job is to what? Let's see here. This would be secant is 1 over cosine squared theta d theta dt equals negative 150 over x squared dx dt. Okay, so now we can use the when info. Oops. Okay, so now we can use the when information. All right, so let's plug in what we know so far. So we know that we're dealing with a triangle, and again, this is kind of nice because they said it's at constant. So this is a right triangle, right? So we have this right triangle like this. Okay, and what would the cosine of this right triangle be? Well, they told us that 300 feet of string have been let out. So this is my when. So if I know this is 300 and I know this is 150, could I find x if needed? Because it looks like in this problem, I'm going to need x, and I'm also going to need to know the cosine, which is adjacent over hypotenuse. So I'm going to do a little bit of scratch work. I'm going to do 300 squared minus 150 squared, and that has to equal x squared in this particular problem, right? So hopefully you guys are okay so far. Now this will be what, 900, let's do this, 300 squared minus 150 squared, and that's 67,500. So second function square root of second function answer. And I get approximately, well, you know what? For some reason, I feel like I should have got a better answer than that. Oh, you know what? I don't even have to do that, actually. Now that I think about it, let's see what we can do here. We know oh, that's why. So we don't have to use a decimal. You know what? I think I could do this a little bit more accurately. Let's try this, guys. Sorry about that. I want to try it the way that I did it in my notes, because it gives me a little bit less of this estimation. So we know, let's go back to the beginning. Sorry about that. That way would work too, but I actually like the way this one works out. So tan of theta, we know tan of theta is worth 150 over x. So that means if I wanted, this is also so this is also true then that cotan of theta is equal to x over 150. And the reason I want to do that, and you'll see why, is this is actually 1 over 150 times x. So that means when I differentiate, I don't have that negative exponent that gets a bunch of the x floating around. So now let's look at it. This means and again, it's these little things. I should have done this from the beginning, but I just figured, hey, how bad can it be? But it actually gets a lot worse. And then you have decimals from here on out. So what I'm going to do is I'm going to do cotan of theta equals 1 over 150x. Okay, now I can ddx both sides, or ddt, I'm sorry. I don't know why sometimes I use brackets and sometimes I use parentheses. So that would be that. Now here's why I did it. This is the cleanup. This is what makes it a little bit nicer. So the derivative of cotangent, you guys know, is negative cosecant squared theta. That would be the normal derivative, but because it's with respect to t, we attach the d theta dt, because remember, we're taking the derivative of theta as well. And now this will become 1 over 150 times the derivative of x, which is just 1. Okay, For some reason, I think on my calculator, maybe it would have worked fine and my calculator gave me an ugly answer. No, that's not what I had anticipated. Okay, so now let's see here. They tell us, oh, but hold on. What's the derivative of, I almost forgot. We just took the derivative of x, which was 1, but it was with respect to t. So we have to attach the dx dt. Sorry, I was checking something on my calculator real quick, you guys. So we get dx dt. All right. So now the thing is we can finally do cleanup. Once you've taken the derivative, now we use when info. Okay. So first of all, cosecant squared. Well, this is really, you guys all know that cosecant, let's do it over here on the side somewhere. Cosecant theta is worth hypotenuse over opposite, right? So what I'm going to do is I'm going to look at my hypotenuse, which is 300. So this is 300 over my opposite side, which is 150. And then it's negative. And then, oops. It's negative outside. And then you square that, right? Because it's cosecant squared. Then you put the negative on the outside of the squared. You don't square the negative as well. D theta dt, we don't know. That's what we're trying to find, right? And then dx dt, we know is worth 10, I believe. Yeah, they tell us that dx dt is worth 10. So this becomes 1 over 150 times 10 over 1. We can cancel the zeros. So now this cancels and becomes 2. So this will become what? Negative 4 d theta dt is equal to 1 over 15. So then I have to multiply both sides by a negative 1/4. So we're going to get over here d theta dt is equal to negative 1 over 60. And that will be our rate of change of our angle. So this is the rate of change that this angle is changing by right here when 300 feet of string have been let out. Okay, so at that moment in time, that's how fast the angle is changing. If you could freeze it, that's how fast it would be changing at that moment in time. So once again, normally any problems like this, word problems that involve sine, cosine, and tangent on top of derivatives are normally harder. And in this case, I really think that turning this into an x to the positive 1 power instead of using the x to the negative 1 by converting it from tangent to cotangent helped us a little bit, because otherwise we would have had to deal with decimals and we wouldn't have got this nice clean answer at the end. Okay. All right, so let's try one more. So it says a 20-foot long ladder leans against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 6 feet per second, at what rate is the angle between the ladder and the ground changing when the top of the ladder is 12 feet above the ground? So why don't you guys go ahead and pause the video. This one I didn't draw a picture. I want you guys to draw the picture. Pause the video and try to figure this one out and figure what formula you're going to use to relate everything. What equation will you use that relates? So go ahead and pause the video and get started. Okay, so hopefully you guys are back. Okay, so let's I'm going to draw a picture. So hopefully you guys drew something like this. You got a ladder leaning against a house, right? So here's your house, right? Here's a window. And then we got our ladder right here, leaning against the house, okay? Now they say a 20-foot long ladder. So this is 20, and that's a constant, right? Because 20 feet, the ladder's not going to change length. If the bottom of the ladder slides away from the wall at a rate of 6 feet per second. So we know dx dt, and again, I normally call this x and this y. You could call it a and b if you want, but because sometimes we deal with x and y axis problems, I wanted to do that. I like to use x's and y's, x for the left to right and y for the up and down. So dx dt, it follows if the ladder slides away from the wall at a rate of 6 feet per second. So this is 6 feet per second. You could just write 6. At what rate is the angle between the ladder and the ground? So that's this right here. That's theta. The ladder and the ground changing when the top of the ladder is 12 feet above the ground. So we now know when And this would be y equals 12. So this is 12 right here. Okay, and I think that's all they gave us, right? So let's see what we got here. Okay, so what equation is going to relate? Okay, well, first things first, if needed, I want to be able to find x, right? So x equals what? Well, because we're going to need to use when information to find x, that makes x also when information, okay? So I'm going to do 20 squared minus 12 squared is equal to x squared. So this would be 400 minus 144 equals x squared. And this is what, 256, which I'm assuming is 14 squared, but let me just make sure. Oh, no, so then it's 16 squared. And that's 256. So that means that 16 is equal to x. So we actually know that this is 16 as well. But that is actually when information because I used the y equal 12 to find it. So if you had to use y equals 12, which is when information to find another value, that makes that other value now when information. Okay, so we can't use any of this until after we've differentiated. So let's find an equation that relates. So I once again have sine theta, cosine theta, or tan theta. Now, how do I know I'm using sine, cosine, or tangent? Because we're looking for theta, and that relates side lengths and angles together. So sine, let's see what would sine be. Sine would be opposite over hypotenuse. Oops, can't use 12. Opposite would be y over y over hypotenuse, which would be 20. And that would give us, we would end up with a dy dt. Not good, so we can't use that. Cosine of theta would be adjacent, which would be 16, not 16, which would be x over 20, which would lead us to a dx dt, which is totally fine. We can't use tangent, by the way, because tangent would be y over x, and we'd end up with a dy dt once again. So we're not going to use tangent. So this is our guy. So this is, I'm just walking you through the process on how I decide. So I'm going to take cosine of theta as my equation that relates, and this is going to be 1 over 20 times x. I like to write the fraction off in the front so it makes it look like it's a constant multiple rule better. Okay, so now we're going to ddt both sides. Take the derivative with respect to time. Okay, so hopefully you guys did this. Now the derivative of cosine is negative sine theta, but we have to do the chain rule, and this would then be d theta dt, right? We're doing this inner function, and that equals 1 over 20 times 1, which is a derivative of x, but then we have to do dx dt. So very similar to the previous problem we did. So let's see here. What would sine of theta be now that we can use our when information? So now we're going to say use when next. So now that we've taken the derivative, we can now use our when info. So let me see, sine of theta would be SOHCAHTOA opposite over hypotenuse. So this would be 12 over 20 d theta dt equals 1 over 20 times dx dt, but they told us dx dt is 6. So let's do a little cleanup. So we got 3 over 10 there. This divided by 4 would be 3. This divided by 4 would be 5. So I'm going to multiply by the reciprocal. So this will be negative 5 over 3, negative 5 over 3. Okay. So now these will cancel and these will cancel. Is that right? Sure. Just double checking. So this will be 1, this will be 1, this will be 1, and this will be 1. Well, okay. So this will be d theta dt is equal to, oh, I'm crazy. Of course it'll cancel. It's the reciprocal. I did that on purpose. Okay, I'm sorry, I lost track of my own work. All right, so then this will cancel with this, and this will be 2, and this will be negative 1, and then this will cancel with this. So we end up with negative 1 over 2. And that is how much our angle is changing from here to here, right? Oops, let me do this. So our angle is changing at negative 1/2 radians per second. Okay, so again, these are some of the harder problems when you use sine, cosine, and tangent. And I just kind of wanted to give you guys a little video on some of the harder ones that you can use an example. Definitely test caliber questions. I love ladder problems. I love sine, cosine, and tangent problems for Calculus 1 classes. This one might show up, but maybe it would be something with similar triangles, but not necessarily the cone. But just to give you guys a heads up, these are 3 of the harder variety of problem, and these last 2 are kind of similar, and I really like these. But that's going to do it for this video. This will be the last video for related rates. Thanks for watching.